Hello, Algebra 1 students. Today we're going to be going over the Unit 5 activity, the Unit 5 unit review. So that's going to be at the very back of the packet. And if you can go ahead and turn there now, hopefully you've done the rest of the packet up to this point. If you haven't done that, then you're not ready for this video. So go ahead and finish the rest of the packet where you do all the book work and all that, and then come back to this for the review. So with that, let's go ahead and get started and working on the review. It starts, I believe, on page 63. Yeah, page 63, it looks like this. And basically everything I write, you should be writing down, okay? And everything I tell you to write, you should be writing down, okay? So let's see, take a look at graph A and graph B below. Explain clearly in your own words which graph, A or B, represents a stronger linear relationship. Then name the two real-world variables, x and y, from units 4 and 5, or your own hypothesis that are likely to have a positive slope linear relationship together. Okay, so which of these graphs, A or B, have a more linear relationship? Okay, linear has the word line in it, right? So which graph shows more of a line, basically? Hopefully you can see that that would be graph B. So we want to basically say that graph B represents a stronger linear relationship. So graph B, B dot dot dot. I'll let you finish the rest of that in your own words. But basically graph B shows a stronger linear relationship than graph A. Graph A doesn't really show a linear relationship at all. Okay, so it shows no correlation between the X and Y. This shows a strong positive correlation, right? So as the X values go up, you could see the Y values going up as well. So this is a positive relationship, a positive correlation, because you can see as you go from left to right, this would be a positive sloped line that kind of follows this data. So what kind of variables could these be? Well, you could basically put anything you want as long as whatever the X variable is, as X increases, Y also increases. So you could have the x-axis be the height of people and the y-axis be shoe size, right? So this is basically saying that as you measure someone's height, if they have a taller height, likely they're going to have a larger shoe size, right? So that would be a relationship that is positively correlated. So that's one example you could use here, right? But that's not the only example. You could think of 100 or 1,000 different examples for this. Basically, anything where you could say, if this increases, that also increases. So for example, you can say perhaps education level and income, right? So those are positively correlated as well. So that's another example you could use. Okay, so or you could think of your own example. And I want you to just explain, first of all, that graph B has a positive linear relationship, and then explain in your own words an example that could have this type of relationship. Okay, and I've given you a couple examples already. You can come up with your own or use one of the ones that I mentioned. So you'd want to just explain that in a couple sentences. Okay, on to question 2. Recall the data we looked at examining the number of songs in a person's music library, X, and the number of bands they can name in 5 minutes, Y, using the computed derived function equation of y equals 0.01x plus 16. Fill in the table below using this function. So this is a situation that we went over in the very beginning of the unit. If you don't remember, that's not a big deal. But basically, these are going to be your X values over here on the left, and then your corresponding Y values. And we're just going to be using this function here. So first, let's see, if you have some number of songs in a person's library, if they have 200 songs in their library, we can predict the number of bands that the person can name. And the way we would do that is we would simply replace 200 in this equation. We're going to replace x with 200. You see that? Because this is the x variable. In this case, 200. So it'll be y. So to find this answer here, you'd do y equals 0.01 times x, which in our case is 200 for this first example, plus 16. So what we do first, and so this would be y equals, so we do 0.01 times 200. Okay, well that's what, 2? Yeah, 2. So this is 2 plus 16, which equals 18. So with an x value of 200, the corresponding y value is 18. Okay. So I want you to try to figure out this one here and this one here. You're going to be using the same equation. You're just going to replace x with 0 for this one, and then replace x with 800 for this one. Okay. So try those on your own. Next, I'm gonna go over how to find this one here. Okay, so in this one's example, they give you the y value and they're asking you to find the x value. So in this case, they're giving you that y is 46. So what we would do is in this equation, we would replace y with 46. So that would be 46. Again, replacing the y in this equation with 46 equals 0.01x plus 16. Now, again, we don't know what x is in this example, right? We don't know what x is yet. We just know what y is, and we're going to eventually find x. So now we want to solve for x here. So what we do is subtract 16 both sides. Again, we're trying to get x by itself. So then on the right side, we still have 0.01x. So 0.01 times x, essentially, equals, and then on this side, that equals 30. Then, to get x by itself, you divide by 0.01. Divide by 0.01. So that'll give you that x equals 3,000. Okay. All right. So this next one down here is just like the one we just did. So they give you the y coordinate and they're asking you to find the x coordinate. So it's very similar to what we just did. This number will be bigger, right? Because notice the y value is bigger and these are positively correlated. So, and then, yeah, you should be able to do this one as well. Okay, so you should be able to do all the rest of these. The ones on this side are like what we did on this example. And then this one over here is like what we did on this example. Okay, so it's 3,000. Okay, cool. All right, give those a try. See if you can do them on your own. Okay. Question 3. Follow along as I read aloud. Sometimes social scientists choose to look for a difference between two groups of data instead of looking for a linear pattern. For the text messaging versus homework hypothesis we discussed in Unit 4, you could have looked at it in a different way. You could have had two groups of students, both measured on homework time. So group 1, students that send more than 50 text messages per day. Group 2, students that send less than 20 text messages per day. Okay, so group 1, they send 50 or more texts, and you could see for these students, you could see how much homework time they do, right? So this first person spent 45 minutes doing homework and so on. Now group 2, they send less than 20 texts per day. Okay, and you could see the amount of time that these students have spent doing their homework. Okay, so now what we'd want to find is we want to find the mean of both these groups. So let's go and for group 1, we're going to find the mean of this set of data. Now, the way you find the mean is you simply add them all together. So what we do is add them all together, add them all, and then you divide by how many there are. So in this case, we're going to divide by 6 because there's 6 data points. So you add up, you find the sum, and you divide by the total number of numbers. All right, and this gives you the mean. Okay, so that's how you find the mean. Okay, this 6 can change. In our case, it's a 6 because there's 6 data points. But if there was 20 data points, you'd divide by 20. Okay, however many data points there are. Okay, so let's go ahead and do that. So 45 plus 32 plus 25 plus 75 plus 60 plus 50 equals, hopefully you got 287. Divide that by 6. And the mean here is 47.83. And you should see on your calculator that 3 is repeating. Make sure I put my data in correctly. All right, cool. All right, now I want you to go ahead and pause the video and see if you can find the mean of this group. So that's the same as the average, by the way. So when they say a mean, that's the same as saying the average. So the average amount of time that these students spent on their homework is 47.83 minutes. Now see if you can find the mean or the average of this group. Okay, so go ahead and pause the video and do that. Okay, hopefully you got 73.5. Okay, so as you can see, the students that sent less than 20 texts, you can see that they spent more time on their homework on average, right? On average, this group of students spent more time on their homework than these students. Okay, calculate the mean for both groups of students. We already did that. And then write a sentence describing which group had a higher mean and was more efficient in studying and doing their homework. Okay, so I think you could do that on your own. So looking at these, who had the higher mean, and what does that tell you about texting and the amount of homework done, right? So you could say something like, sending more texts generally means less time spent on homework, right? The group that sent 20 or fewer texts, they spent more time on their homework. Okay. Question 4. Decide if you would use the mean or median for the best measure of central tendency for real estate prices below from a neighborhood in San Diego, California. You must calculate both the mean and the median of the data and then specify which measure represents the data the best and why. Okay, so let's go ahead and find the mean. Hopefully, you should be able to do it on your own. So go ahead and try to see if you can find the mean, and I'm going to do the same right here. Hopefully we can get the same answer. So 800,000 plus 780,000, 840,000, 855,000, 795,000, 810,000, 455,000. Then divide by 1, 2, 3, 4, 5, 6, 7. Divide by 7 because there's 7 items here. So the mean, that would be 762,000 143. We're going to round to the nearest dollar here. Now the median means the number in the middle if they're listed from least to greatest. So if these numbers are listed from least to greatest, we want to do the one in the middle. That's how we find the median. So I'm just going to cross off the smallest and the largest as we go. So first, the smallest is this number. Now I want to cross out the largest here. So the largest here. Then the smallest after that is 780. And then the largest after that is 840. Then the smallest, then the largest. Okay, so 800,000. 800,000 is the median. Okay. So it's the number in the middle, like it's the middle value, basically. It's the value that is in the middle when put to least to greatest. So now you would want to explain which value best represents the center of this data. So what they want you to basically see is that the median is actually a better measure of this. And the reason why is because the mean is influenced a lot by outliers. And in this group, you can see that the 455,000 is an outlier, meaning it's quite a bit different from all these other values. Right? These other values are pretty close to each other, but this one is way far off. So that's what we call an outlier. Now, the mean values are always influenced by outliers. They're always drawn towards outliers. And if you have a set of data that has outliers in it, a lot of times the median is best to be used. So things like housing prices are very commonly, we look at the median and not the mean. So I want you to explain that there, that in this case, the median is a better indicator of the middle of the pack, basically, because the set of data has an outlier in it. Okay, so I want you to explain that there in your own words. Now, this last one is pretty tricky. I'm gonna be honest. This one's pretty tricky. So let's go ahead and work on it. Number 5. Rick just walked into a casino in Palm Springs, and he sees a game he really likes. He likes the game so much that he's ready to risk $1,000 to play the game. Sounds like a fool. The game requires him to flip heads on a coin 5 times in a row. So he's going to flip a coin 5 times, and he needs to get heads every single time in order to win. So if he can do it, the casino is offering him $25,000 from the $1,000 he risks. So he's risking $1,000, but he has the potential to win $25,000 if he can manage to flip that coin and get heads every single time, 5 times in a row. Decide if this is a good or bad deal for Rick based on the rules of probability. If it is a bad deal, you must determine how much Rick is getting ripped off by. You must be as clear as possible in your explanation. Hopefully you realize by now that gambling is not a winning proposition. Okay. So he's willing to bet $1,000 and he's hoping to get heads 5 times in a row. So let's first figure out what's the probability of him winning. So what's the probability of a win for Rick? So we're going to just put win, probability of getting a win. So whenever you see P parentheses and then like a word or something like that, usually they're trying to indicate that this means the probability of this outcome. So this is the way you'd read this is what's the probability of a win, of getting a win, right? So let's go and calculate that probability here. So first, what's the probability on a single coin flip? So just flipping a coin once, what's the probability of getting heads? So hopefully you already know that that probability is 1/2. Okay. But he doesn't need to get heads just once. He needs to get heads 5 times in a row. So we're going to multiply by 1/2 5 of them. So essentially 1/2 to the power of 5. And the reason why is because these coin flips are what we call independent from each other. So when two probabilities don't affect each other, they're independent. So if I flip a coin and get heads, that doesn't change the probability that the next one will be heads, right? So if I flip a coin and get heads, well, that happens half the time. Well, the next time I flip it, it's going to be heads half the time again, right? Because getting heads in the first flip does not change the probability of getting heads in the second flip. So since those probabilities don't change each other, we call those independent. Now, if you have a bunch of independent events that you want all of them to happen, what you do is you'd multiply those independent events together to figure out the probability of them all happening. So in this case, the probability of getting heads times the probability of getting heads times the probability of getting heads 5 times. And we multiply those together because these events are independent and we want them all to happen, so we multiply. Okay, so let's go ahead and multiply that together. So when I multiply fractions, I multiply the tops. Okay, well, 1 times 1 times 1 times 1 times 1 is 1. All right, and then we multiply the denominators to get the final denominator here. So 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. So the probability of him winning is 1 out of 32. Okay. So we want to write that in a sentence. So the probability, I want you to write down, the probability of Rick winning is 1 out of 32. So go ahead and pause the video for a second and write that down. Okay. Now, so what does that mean for Rick? Well, if he risks or wages $1,000, how much should he win in order for the game to be fair? Well, if he's risking $1,000 and the payoff happens 1 out of 32 times, then $1,000 wage should have a payout of 32,000, right? So if $1,000 wage and this probability, if you want the game to be fair, the payout should be 32,000, right? Because essentially, imagine he played the game 32 times, right? Imagine he played this game 32 times. Chances are he would win once, right? That's how many he would expect to win. It's just once. So if he played the game 32 times, it would cost him 32,000. And since he would be expected to win just once, the payout should also be 32,000. I hope that sort of makes sense. I guess maybe instead of a period here, we should add to that. $1,000 wage should have a payout of 32,000 in order to be fair. So then the other part of the question asks, how much is he getting ripped off by, right? Rick is getting ripped off by. So since 25,000 is the payout of this game, he would be getting ripped off by 7,000. He is getting ripped off by 7,000, right? $7,000. Okay. When it comes to gambling at a casino, it's pretty much every single game is in the casino's favor, right? So, yeah, whether it's the slot machines or playing the roulette table or any other game in the casino, they are all at least slightly giving the casino an advantage. All right. Well, I hope that made sense. Hope you're able to get through it. And if you have any questions, you can feel free to email me. My email is ttrigg@ofy.org. All right. Well, with that, take care and good luck on the test.